Every day at the Virabhadra temple, tourists perform a simple test. They slide a thin cloth completely under a massive granite pillar. That pillar is a solid 20-ton block of stone. Logic says a rock that heavy should be planted firmly in the ground. Viral videos often use this moment to suggest anti-gravity magic or levitation. But a closer look at the far corner reveals a different story. The cloth gets stuck because the pillar is tilted, with one edge resting on the floor. Finding a pillar this far off the ground raises a question. Was this a massive oversight by the 16th century stonemasons, or a deliberate piece of engineering? To find the answer, we have to look at the people who built this. The temple was commissioned in the 1530s by two brothers, Virapana and Virana, under the Vijayanagara Empire. They designed the Natya Mandapam, or dance hall, with 70 intricately carved pillars supporting a sprawling stone ceiling. Granite is incredibly dense and difficult to shape. Quarrying, transporting, and balancing this volume of rock without modern industrial cranes required absolute mathematical precision. Architects operating with that level of geometric mastery do not accidentally cut a main support column a few inches too short. In this part of Andhra Pradesh, the builders had to contend with a recurring problem: ground-shaking seismic activity. Stone is incredibly strong under vertical pressure, but it lacks the flexibility to survive the side-to-side forces of an earthquake. The solution lay in the principles of Vastu Shastra, an ancient Indian system of architecture. It dictates that to survive tremors, a heavy stone building must be able to move with the earth. Instead of building on bedrock, they laid thick layers of river sand beneath the platforms, acting as a shock absorber. Above the foundation, architects used mortarless, interlocking stone blocks. When the ground shakes, these joints slightly slide apart, then neatly settle back into place. The entire temple was engineered as a dynamic kinetic system, a structure that accommodates lateral shock rather than resisting it. This kinetic design is the reason for the hanging pillar. This specific column was never intended to hold the roof up. Its role is to pull the roof down, acting as a central balancing counterweight. As this schematic illustrates, an earthquake causes the massive stone roof to sway. Because this pillar is suspended from that roof, it acts as a pendulum. As the ceiling shifts one way, the heavy granite pillar sways in the opposite direction, stabilizing the structure. Leaving the pillar disconnected from the floor was a deliberate application of mass dampening. During the pre-independence era, a British engineer visited the site, frustrated by the local legends surrounding this magic rock. Convinced he could uncover a trick, he brought in iron crowbars and tried to forcefully dislodge the pillar to study its support system. The moment he wedged the pillar out of alignment, the stone roof and surrounding columns shifted, threatening to cave in. He suddenly realized the floating rock was the central anchor keeping the entire hall balanced. He abandoned the experiment immediately. But his intervention left the pillar permanently tilted, resting on that single corner. That mechanical shift created the illusion that tourists see today. By trying to debunk the pillar, the engineer inadvertently provided the proof of its structural necessity. Modern engineers use a similar concept in skyscrapers today. Massive pendulums called tuned mass dampers that stabilize towers against wind and tremors. The builders of Lapakshi mastered these mechanics of seismic resilience centuries before modern science caught up. Today, curious visitors still kneel on the stone floor to slide fabric through that dark gap at the base. That space beneath the stone is a record of an ancient solution, a piece of technology built to survive forces that modern engineering is only beginning to master.